In the previous video we saw a number of components that were resistors of some description. In this video we're going to have a look at that property of resistance and identify what it is and why it's important to consider. And the first thing to identify is what resistance is really about. And it's a property of a substance that restricts the flow of current through it. So it's not the definition as such, but it's a good way to think about what resistance is and why it's relevant in a circuit. So it restricts the flow of charge, and when we're talking about charge we're really talking about currents, and so restricts the flow of current through it. And the way that that restriction of current occurs is because electrons moving through the substance will transfer some energy to the atoms in that substance, and so there's kind of a friction between the electrons and the atoms, and as a result it makes it harder for the current to pass through. The way that resistance is defined in the syllabus is from an equation, and so we're just going to write that equation, and it's basically just a ratio of the voltage or the potential difference across a component divided by its current. So there's the definition of resistance. Note that it is the voltage divided by the current. It's not the change in voltage or the change in current. It's just V divided by I. The symbols that we're using there are important to note again. So R is the resistance in ohms. So it's spelt OHMS, and the symbol for it is the Greek letter omega. V is the potential difference across that resistance, and as we know, potential difference is measured in volts, and I is the current in amps. So there's the definition, as I said, for resistance. A more common form, the way that most people engage with this idea of resistance is the idea of Ohm's Law. So that's just a rearrangement of that equation, and it's expressed in this way: V equals Ri, and it just gives us a relationship between the voltage and the current when we're considering a resistance. If we have a component that has that type of relationship, so in other words that has the potential difference across it being proportional to the current, then it's considered to be an ohmic conductor. So if it obeys Ohm's law, it's an ohmic conductor. To make sense of that, we'll have a look at a simple circuit in Yanker and identify what that really means in terms of voltage being proportional to current. So here's a very simple circuit with a resistor of 100 ohms. We have it connected to a 0-volt rail and a variable voltage supply which can go up to a maximum of 10 volts. You'll notice on the right we have a graph that's graphing voltage on the vertical axis and current on the horizontal axis. So as we start to increase that variable voltage, you notice that the current increases as well. So in this case we can see that there's a directly proportional relationship between voltage and current. The reason why I've graphed voltage on the vertical axis and not the horizontal is so that we can see that relationship V is equal to Ri. Now if we look at a point on that graph and consider what the voltage is and the current, so this point here, a voltage of 5 volts produces a current of 50 milliamps. If we take the voltage divided by the current, we'd find that the answer would be 100 ohms. We could do that for any point along this line and we would always find that the answer is 100 ohms. So the gradient here gives us the resistance of the component. So you can see there that the directly proportional relationship V equals Ri shows us that the gradient is that value R. Now while resistors follow Ohm's law in that V is proportional to I, not all components do. So for any component where V is not proportional to I, we would consider them to not be ohmic conductors, and they would be known as non-ohmic conductors. And there are a number of those sorts of components. The easiest one to identify would be a filament lamp. So we'll have a look at that in Yanker, and we'll have a look at a few others in class. But the main thing here to be aware of is that if there is not a proportional relationship between current and voltage, then the component is considered to be a non-ohmic conductor. You can now see in this circuit I've replaced the resistor with a 10 watt filament lamp, and we still have the same graph, voltage on the vertical axis, current on the horizontal. Notice that the horizontal axis scale has changed. Now as I start to increase the voltage across the filament lamp, you'll notice that it is not a linear trend line. So that means that it definitely is a non-ohmic component. Now to calculate the resistance, we'd still use that definition that we saw earlier, voltage divided by current. So for example, at this point here, 1 volt over 200 milliamps would produce a resistance of 5 ohms. If we move all the way to the end, 10 volts appears to have a current of about 760 milliamps. That would give a resistance of about 13 ohms. So you can see there that the resistance of the component depends upon the potential difference across it and the current flowing through it.